Hello, students. Shh. First of all, look left, look right, make sure we're alone, because what I'm about to tell you is top secret. In fact, I had to come here to the lab in the middle of the night to record this video. So first of all, make sure that no one else is watching. If they are, just hit pause and watch this video some other time. Okay, if you're really alone, I have some secrets to tell you. Actually, more than one. And the reason why they're secrets is there are some very special reagents that only licensed chemists are allowed to use, or really even to know about. And so I might be breaking the IUPAC rules on secrecy by divulging this information, but I know that hardly anyone ever watches my videos, so probably this information is safe. But just in case you are watching, check this out. So here are 3 secret reagent things that you can use to do some more special organic synthesis. Let's look at the first one. The first one is called LDA, or lithium diisopropyl amide. Let's suppose you start with this compound right here, 2-chlorobutane, and you add some OH minus, because what you're trying to do is eliminate that chloride and get to an alkene, okay? Normally that's a little bit tricky. Why? Well, right, what's my substitution here, my haloalkane? It's in fact secondary, right? I know that primary haloalkanes, when you add hydroxide, tend to substitute. Tertiary ones tend to eliminate. This one is secondary, so unfortunately, I'm going to get a mix of different products. I'm going to get some of that elimination product and also some substitution product. But what if I don't want both of those? What if I only want one? What if I only want this elimination product? Well, guess what? That's where LDA can help you out, okay? LDA, if you add that instead of hydroxide, LDA is also a powerful base, but it's got some big old bat wings. LDA looks a little bit like this. That lithium ion is just a spectator ion. It's not really messing with anything. But this nitrogen with a negative charge is a powerful base. Those big old bat wings provide a lot of steric hindrance. This thing can't come around and do a backside attack. So it does not give you any substitution at all. So with LDA, you get none of that. And you get almost 100% of the elimination product. So it's a useful reagent anytime you want only a base to give you elimination. It still does not work with primary haloalkanes. Nothing will eliminate primary haloalkanes, so do not use it on primary haloalkanes. But you can use it with secondary and tertiary ones to give you the elimination product, E2. Let's look at our next special agent reagent. Let's suppose we have this compound right here, and we want to substitute and take off this OH minus and substitute a Br on there. We know how to do that, right? HBr will, being an acid, will substitute OH and put a bromine on it. The problem is something else happens as well. If we just use HBr, what's going on the left side of the molecule? It looks like there's an ether over there. If you remember, strong acids like HBr will take an ether apart. So if you use HBr in this sucker, then you're going to get like Br. You're going to get a whole mess of stuff, right? Like that. Let's suppose you don't want that. Let's suppose we want to keep this ether intact, but we still want to substitute this. PBr3, or phosphorus tribromide, is going to come to our rescue. If we use that instead, this is not a strong acid, so guess what? It does not touch this ether. So, PBr3 replaces or substitutes primary alcohols and puts on a bromine. Still only works if they're primary or maybe secondary, does not work if they're tertiary. Right? Remember, if something is tertiary, you can't do SN2 on it at all. So this only works for primary and secondary. This, the last one is thionyl chloride, SOCl2. This does the same thing, except for chlorines. So just like HCl would also pull apart this ether, if we add this thionyl chloride, SOCl2, it will substitute this. We'll get 100% of that. Something else that thionyl chloride is used for is making those acyl halides. Acyl halides, you will recall, we used in electrophilic aromatic substitution, the Friedel-Crafts acylation one. We talked about them, but we didn't talk about how to make them. This is how you can make one. You start with an acid, you add SOCl2, and that actually converts this into the corresponding acyl halide, right? Pretty slick, huh? In fact, I have typed up all of this in this little handout called Secret Agent Reagents. So if you get a minute, check it out, but don't tell anybody.